Great. So we were talking last time about numerical techniques for solving 0D lump capacitance problems. So we have a problem where there's no temperature distribution in space. There's only a temperature that's a function of time. And we went through a couple lectures ago developing analytical solutions for that. Last lecture on Friday, we went through the first set of numerical techniques that you can use. So there's the obvious ones we can flip back. There's the ones like Euler's technique here, where you are just evaluating the derivative at the beginning of the time step and then using that to step forward to your next node, j. We talked about Hoynes' method, which is here. Hoynes' method is using two estimates of the derivative, one at the beginning and one at the end. So you take what's called a predictor step for your temperature, evaluate the derivative at your predicted temperature, and then go back and correct that using the derivative evaluated at the beginning and at the end of the time step. Right? So this one is sort of using current information. This one's using predicted information. And somehow that's supposed to be a little bit better of an estimate for your derivative here than if you just took one or the other. And so that's Hoynes' method. We talked about the Runge-Kutta method, which involves a bunch of different estimates. So we have 4 different estimates of the derivative, which we call AA, BB, CC, and DD. And we're doing that at different positions, either at the start, at the end, or at the half node position. Right, that's what we're doing there. And again, it's supposed to be a better estimate by taking some weighted average of the derivatives, preferring the derivatives taken at the middle node. Okay, so that was Runge-Kutta. Yeah, Liz?
On your plot, you don't have a DD indicated. Where would DD be?
Oh, okay, so DD is going to be the derivative taken at tj plus 1, or t hat j plus 1, time j plus 1. So that's going to be here. I guess I could fix that. So that would be, I don't know what color to use now. We'll make another red one here. So that might be like at this point. All right. Good question. Thanks. OK, Runge-Kutta, it's 4th order. And again, as we're going through these, there's different, we talked about the different errors that were involved and like the different number of nodes that are needed to solve these and went through the example for that. Fully implicit does the same type of thing where you're just evaluating at the end of the time step using the temperature at the end of the time step. So it's not even a predicted temperature. It's just the temperature at the end. Makes it implicit. And then where we left off was not getting to this Crank-Nicholson. So let's start now by talking about Crank-Nicholson. We have, this is our last, say, like conventional numerical technique, and then we have the integral techniques that we'll also talk about. And then I think we'll get to the next topic, which is transient conduction, right? 1D transient conduction. OK, so Crank-Nicholson. So first, we were doing some classification. This is a second-order technique. Second-order technique, and it is implicit. Right, so you're going to expect to see the temperature appearing on both sides of the equation. So the way this method works is we're going to evaluate to get to tj plus 1 by taking tj and adding 2 estimates of the derivative. So this is going to be over here. It's going to be d temperature, d time, evaluated at time equals tj, or sorry, temperature. Temperature equals tj, time equals tj. And then we're also making an evaluation dt, temperature at temperature j plus 1, time at time j plus 1. And that would be times the time step, delta t, divided by 2. Okay, and this is going to be for, I guess, j equals 1 to m minus 1. OK, so you can kind of see what we're doing. Right? We have basically Euler's technique, right, this first part. And then we have fully implicit technique here. And we're just adding the two together and taking the average. So just a combination of stuff you already have thought about. So what to say about this? I guess when it comes to evaluating it, so we could write out for our example up here, this guy in the corner. So we could write out what this looks like. It would be tj plus 1 equals tj plus evaluating this would be T infinity at time j minus temperature at time j divided by tau LC, our lump capacitance time constant. And then the other evaluation would be T infinity at time j plus 1 minus, so I'm going to move this out of the way, sorry. Minus temperature Tj plus 1, again over tau LC, times delta T over 2. So we have this, if you're going to implement this in ease, you can just take this equation and plug it in, no problem. It'll solve it with the implicit relationship, because we have Tj plus 1 here, and we have Tj plus 1 here. But again, it's not a problem for ease. If you need it to be explicit for, say, a Python implementation, you're going to have to solve this equation explicitly for Tj plus 1, which we can do. I don't know if it's worth writing out, but I guess you can take my word for it. It's just algebra to solve for it, and you can get that. So let's look at how that's implemented in the Python code. Where am I here? Podium computer. OK. So looking at this in the Python code, again, here's our same file that we had before, just to refresh you. We have our analytical solution that we're plotting. That's here. That doesn't change. We have our function T infinity, which is some polynomial. And then we're choosing these different methods. So what's this one? This one is Crank-Nicholson. OK. So you can see down here how this is implemented. I guess it's right here. Move this out of the way. So Tj plus 1. And then what you have on the right-hand side is the explicit solution for that equation that we wrote previously. So again, just take my word for it. It's the explicit solution. But what you should see is on the right-hand side, there is no temperature Tj plus 1. Right? That's only appearing on the left side. There is time Tj plus 1, but that doesn't really matter. I mean, we know what the time steps are going to be beforehand. So we can plug in our next time step. It's a predetermined matrix that we're using for that. We solved it this way. OK, so if we run this, hopefully, again, this runs. Run. Where is my plot? Here we go. So it does pretty well, right? We're looking at the red dots being the analytical solution, the black being the ambient temperature, and then the green is the analytical solution, and our red dots are the numerical solution. So the red dots are pretty close. Our maximum error is about 1. Average error is a little less than that. And compare that to what Euler's method, which was like 8 Kelvin, if you remember. So OK, it does pretty well. We could go back and add more nodes again and just see at what point it becomes really good. Maybe 21 is a good thing to run. So 21, we see the error is reduced down to 0.25. So that's telling us what? That's second order, right? We doubled the nodes, but it's error is going down by a factor of 4. So it's second order. Right, so you can kind of see how this plays out.